Okay, so this is part 2 of the video introduction to section 2 of chapter 10 for polar coordinates, and this is where we left off. So we left off sort of pointing out that we have a little formula we can use if we have polar coordinates and we want to convert them into Cartesian coordinates. And similarly, we have a sort of formula we can use if we have Cartesian coordinates and we want to convert them into polar coordinates. All right, so now let's look at this a little bit more graphically. All right, so with our Cartesian system, again, helping us transition to polar, let's consider Cartesian first. How do we usually end up with graphs? Where do these points sort of come together? Usually the reason we have a graph in a Cartesian system is that we have an equation relating the two variables together. So for example, a simple example might be that you have y equals x squared. And so there are pairs of values that are solutions to this equation. And you could imagine making some of those pairs of values by sort of starting with an x value, seeing what corresponding y value would work with it. And then if you do this a couple of times, you start to get points. And if you plot these points, then you can sort of connect the dots to imagine what's going on with the graph. And then you can connect that these are solutions in point form to a particular equation. Everything that makes that true will be on the graph, and any points on the graph are an x and a y value in the Cartesian coordinate system that makes this true. And again, in order to find points quickly and easy, like if I want to find this point where x is -1 and y is 1, then the graphing grid system helps me because I identify a solid line on my graph paper, and those are all the places where x is -1, and a solid line is there where y is equal to 1, and then I can find the point where those meet in order to make the graph. So if we are, instead of getting horizontal and vertical positions for our variables, but are instead getting an angle of rotation and an r value of distance traveled out to the point, well, then things look a little different. So just while we're still here, if instead I want to have an r theta and I want to look that up, well, I might want to say, well, first I'm going to rotate at a particular angle of theta. And so I want to be able to find that. So I know, for example, that here this is where theta is equal to 0. And I know up here this is where theta is equal to pi over 2, just because of our work with trig. And over here we have pi, theta is equal to pi. So I can imagine rays pointing out from the center in a particular direction being all of the points on the graphing system that have that particular angle. So for example, if I point out in this direction, then I'm at an angle where theta is equal to pi over 4. And if I sketch this in now, then at any point in the future, if I need to find that angle, I can say, oh, it's that solid line right there. So instead of having lines from left to right and up and down, as you would in our Cartesian graph, we would like rays swinging out from the origin at particular set angles so that we can then go and find the one we want in order to identify the point. Then, in addition to that, we'd next want to look up a set r value. I need to leave the origin and travel along one of these rays some amount, like r. If r is 1 or 2 or 3 or 4, I would like those constant values. So, for example, if r is equal to 1, well, where are all the points when r is equal to 1? Well, those are on a circle that's 1 away from the origin. So if I draw a little unit circle here that goes to the point 1 down, 1 to the right, 1 up, or 1 to the left, I get the unit circle, and those are all the points where r is equal to 1. Similarly, if r was 2, then I would either be down here or over there or up here or over there, speaking to the picture. And so that second circle are all the points where r is equal to 2. And so if I'm going to make a graphing grid for polar coordinates, I don't want the up or down lines. I want radial rays out from the center, and I want concentric circles for various r values that are fixed. And so that's how you get graphing paper for polar coordinates, and then we can consider making polar graphs. So, sort of having to describe the rationale behind it, we can now switch. So let's clear all of this, clear all the contents, and now let's switch from Cartesian coordinates to polar coordinates. And now we get a graph paper like this. So this is what graph paper looks like if you're graphing in polar coordinates. It's a little tight. Maybe I'll zoom in here somewhat. There we go. And so this is graph paper for polar, and what would we be graphing? Polar points. And how would we choose those? Because they satisfy a polar equation. So again, just to be sort of start with simple, let's say you had a fixed theta value. So let's say theta is equal to pi over 6. Well, what is this? This is an equation. It may be true, it may be false. That depends on r and theta. Now, I can make a table of values for r and theta to get my points. Now, in this case, because r is not mentioned, r could be anything. I just need to make sure that the theta value is pi over 6. So I get pi over 6, and r could be 0 or 1 or 2 or 3, and doesn't really matter as long as theta is pi over 6. Fatter lines down. And I can plot points. When r is 0, I'm right at the origin. When r is 1, I need to move in the direction of pi over 6. So again, this is where theta is 0. This is where theta is pi over 4. This is where theta is pi over 2. So then we could sort of imagine some smaller amounts. Pi over 4, if I drop down, this is pi over 6. This is pi over 12. So I would travel along this line, I should say this ray, because those are all the points where theta is pi over 6. And then I can imagine all these points here, a 0, a 1, a 2, a 3, a 4, a 5. They're all on that line. They're all on this equation. And of course, you could imagine making these points and connecting the dots. Just the same way if you had a fixed variable value in Cartesian coordinates, like x equals 7, well, then you'd get a vertical line through all the points where x equals 7. Well, here I get a ray with all the points where theta is equal to pi over 6. However, I'm going to point out something which we didn't address directly before. It is possible, actually, to assign to r a negative value, like -2. And what that would mean is that instead of moving toward the angle, once you start from the origin, you back up instead. So if I'm facing in the direction of pi over 6, but I back up 2 spaces, then I would go to here. So that would be where r is -2, but I still have the angle of pi over 6. And I could go -3, or -4, or -5, or whatever. So actually you get a line through the origin. And if I go toward the angle, those are because of positive r values. And if I back up away from the angle I'm facing, then that means that r had a negative value, but I can still get all those points that way. So that's why you have this big radial line, because then it makes it easy to find any points where the angle is pi over 6. Or I can use this line for pi over 12, or this line for pi over 4, or this line for pi over 2. Similarly, we could imagine that you had a fixed r value. Like let's say the equation is that r is 3. Again, there are points that satisfy this where you have r and theta values. What you know in this case is that it doesn't matter what theta is, it's not in the equation, but r has to be 3, and you can have any angle you want. 0, pi over 2, pi over 3, pi over 4, whatever you want. So where are all the values where r is 3? Well, those are all the points that are 3 spaces away from the origin. If I go at an angle of 0 and I count out 1, 2, 3 spaces, I land here, or here, or here, where I'm just changing the angle, but I'm making sure I'm always at a distance of 3, and so I get this circle. So this is the circle where r is equal to 3. That's the graph of this equation. And all of these concentric circles are fixed values of r so that you can easily get to where r is 3 or 4 or wherever you want to be on your point because those lines are mapped on the graphing paper. So this is why graphing paper is like this in Polar. And the way we make a graph of a polar equation can be sort of as I was just indicating, where you imagine some points. So let's make something a little less trivial where you actually have both variables involved. So let's say we had something like, well, let's do maybe an example, see if they have something I'd like to do. No, not really. All right, let's try this. Let's do a very simple equation that ends up not being as simple as you would think when you try to graph it. Let's say you have r equals theta. R values, theta values. So just like when you first learned how to graph in Cartesian, when you have an equation, it's good to imagine plugging in values for one variable and figuring out what you get for the other. Usually, even though it says r and then theta, and in this case it doesn't matter, most of the equations you will get will be solved for in terms of r, with r in terms of theta. So I could literally write this as, and this will be sort of a common sort of notation, r as a function of theta, where I plug in theta and I see what I get for r. So they'll have an expression on the right that's got a theta in it, and you do something with it, and then the answer you get is the r value. Now, it doesn't have to be that way, and just like you don't have to have f of x, you might have like x's and y's in an equation together, but this is sort of a thing you'll start to see commonly. So if I'm plugging in theta values, theta could be 0, then r would have to be 0. Theta could be pi over 12. And I'm going up through nice values for theta to plug in. That makes r pi over 12, etc., etc. I go to pi, I get a pi, whatever I get. So my first point is 0, 0. And normally with Cartesian, you can kind of like plug in nice x values and go left to right, and you're used to that. But here you don't. You plug in nice theta values, and you imagine rotating around through those angles and plopping down points at the correct r distance each time you do that. So if I go up to the angle where we're at pi, so here's where theta is 0, here's where theta is pi over 12. I'm sorry, I said 12, I put it 2. I'd have to plot a point where the r length from the center is pi over 12. Well, that's not a nice whole number, so I'm just going to approximate. Pi is like 3.141 something. So pi over 12 is kind of like 3/12 or a quarter. So I'm going to adjust my scale like I would on a normal graph. So instead of making this first circle a 1, I'm going to go out 2, 3, 4 circles right here. And I'm going to say this is where the radius is 1. 1, 2, 3, 4. So therefore this would be where the radius is 2. So you can adjust your scale just like you might on a Cartesian graphing system to make the graph a little bit easier. So now I'm going to plot a point where I'm at this angle pi over 12, and a pi over 12 for the radial length is about 1/4. So on this scale, that would be about there. So then that's pi over 12. If I go over to pi over 6, oops, I said 6. So that would basically be twice as far out and twice the angle. So I'm going up to here. So here's pi over 6, and then I'm going to go out 2 radial marks. Because 3.14159 divided by 6 is a little bit more than a half. And let's say, for example, I jump up to pi over 2, just to follow ahead here. Make this a pi over 2. So 3.14159 divided by 2 is like 1.57, something like that. So 1 is here, and I'm going to go 1.57, so maybe about there. So as my angle is rotating this way, I'm imagining this curve is getting sketched out as I plot in these R values, and then I connect the dots with that in mind. So it's something like this. And that each time I went out to an angle, I would get another point along the way until by the time I got up to pi over 2, I was that far away. So then similarly, when I get out to pi, I'll be pi away. So that's pointing directly to the left. Pi is a little bit more than 3, and my units are 4 spaces apart. So here's 1, here's 2, here's 3, and it's 3.14159. This is like 3.25, so it's like here. And so my graph would continue to go out as I rotate it around, somehow trying to find its way to there. Maybe it went out a little faster than that. And you can actually graph in polar pretty much in any TI calculator or on graphing utilities that are not embedded in this annotate site. Maybe if you went to Desmos, I think maybe has that. Certainly Mathematica. And so basically, as the angle gets bigger and bigger, my points are getting farther and farther away from the origin. And so my graph will just continue to climb, and then over here it'll be 2 pi away, and then it'll be 3 pi away, 4 pi away. So it's spiraling outward. It's spiraling outward. So I get this kind of a graph by just plugging in these nice positive angles. And it's, of course, very, very different than what you're used to seeing. Now, I could also plug in negative angles. So just as I pointed out earlier that r could have a negative value, so could theta. We have negative angles in trig, right? You plug negative angles in. You go down from the x-axis instead of up. You rotate clockwise instead of counterclockwise. So, for example, what if I put in negative, we'll say pi over 4 for theta? Well, that means my r value has to be negative pi over 4. So that means to look at the angle negative pi over 4, I would be looking at this direction. Right, here's my place where the angle is negative pi over 4 because I've dropped down 45 degrees. I've gone down 45 degrees to get to negative pi over 4. But then instead of plotting a point in that direction, I would be backing up because it's a negative r value. So negative pi over 4 means that I would be backing up. And what is pi over 4? Again, that's a little less than 1, 2, 3, 4. So maybe if I back up, I'd be 1, 2, 3 of these things, like somewhere around here. And I'd be getting that as I'm sweeping out in the clockwise direction for my theta, I'm backing up from 0 and plotting points over here that go like that. I know this feels very different than what you've done before, and it basically would look just like what I was doing on the positive side, so I think I sketched this out a little bit better on this side. But for example, when I get down to where I'm getting down to the point where I'm at negative pi over 2, I would go backward away from that angle a distance of positive pi over 2, and I'd get right back to that same point that I had when I was going the positive direction. And so that means this graph is going to go up here and meet that there. This graph went out over here and met that there. I erased it. But then it's going to do its own spiral, and it's going to meet down there and then go out. So basically, I have kind of opposite direction spirals that all coexist on the graph. And this is just for the graph that r equals theta, or r of theta is theta. It's this kind of spiral. So I know that's kind of wild. It takes a lot to wrap your mind around it. You have to practice plotting points to get a sense of why these graphs are the way they are and to make them correctly. A good way to do that is to just make a table of values for r and theta, have some polar graphing paper or grid that you can graph onto, find out plug-in values for theta, see what you get for r in the equation provided, and plot those points one at a time, being ready to go downward for a negative angle or backward for a negative r value, starting from the origin. So I'm going to go ahead and do a little bit, couple more examples of this, but again, I'm going to stop this video here, give you a chance to wrap your minds around this, and we'll pick up from where we left off in a little bit.